Okay, now we're recording the class. I have to remember to do this. Let's put a little picture of me up here so that it's not too boring. Whoa, that didn't work. I don't know, maybe it's really boring to have a picture of me up here. Whoa, too big. How do I make this smaller? No, I can. Just don't know how to do it. Oh, goodness. I know there's a smaller view of this, but whatever. Let's just get rid of that. Okay. Anyway, so what we're just saying is that on this problem here, in number 9, part C, we calculate this vertical component of the velocity and horizontal component of the velocity Vy and Vx if the car is going off this ramp at this angle. But in part D, this Vy and this Vx become the Vy0 and the Vx0 for part D when you start using a kinematic equation. Because then you can use the initial height off the table to be 0, and then this would be negative 1.9 meters down at the bottom. Or you could say the floor is 0 and your initial position is 1.9 meters above from the floor, whatever. But in the end, you can use this data, this information they've given to solve this problem. You can solve for the time in the y dimension, and then you can use that time in the x dimension to solve for the distance that it travels. Because you'll be able to figure out from a kinematic equation will help you to figure out how fast it's going at the end here. Another kinematic equation in the y dimension will help you to figure out the time that it's in the air. And then once you have that, you can figure out how far it goes from its velocity in the x direction and the time that it travels. So that's how we go about number 9. And then part E is about directions of displacement. Remember, displacement is like the as the bird flies distance, right?
What about instantaneous?
Instantaneous what?
You're not on that question.
Where?
Second one.
So
B.
in B, right here. So you want to know its velocity right here?
Yeah.
Oh.
How fast
So in that case, they've told you that it's placed on the tabletop and released, so it accelerates across this in 1.01 seconds, right? You know the distance that it travels, and you know how long it travels, and you know its initial velocity. So with that information, with distance and time and initial velocity, there's a kinematic equation that will tell you the final velocity if you know that it's accelerating constantly, which it does. You know which equation that one is? Its final velocity equals, let's see, what is it? Oh, it's the final velocity squared, so we call it V. So Vx squared equals V naught x squared plus 2 times the acceleration times the change in x. So the change in x is the distance across the table, in this case 1.3 meters, right? No, that's not going to help us because we don't know the acceleration, right? We can't use that one, sorry. We have to use one that has time in it because we have the time. Oh, we want to find the acceleration. Never mind, that isn't it. We want to know the acceleration. So it's v. So it is the same one that I was looking at. V0 squared plus 2 times acceleration times delta x. And we want to know how fast it accelerates. And we know. No, this still isn't going to help us because we don't know the final velocity of x. So we want to know the acceleration, right? So this is not going to help us. We need to use this one. The one we need to use is the x. The final position equals the initial position plus velocity initial in the x direction times time plus 1/2 at squared. Right? So in this one, our initial position is the edge of the table on the left, which is 0 position. This one is 1.3 meters away from that. So that we know that one. Our initial velocity is 0. And this is what we want to find out over here, 1/2 a. And we know the t is 1.01 seconds, right? Squared. So we know everything except for the a in this equation. So we go ahead and take this equation, we solve it for a. So with the 1.3 meters in here, we'll have x will be a number we know. X0 will be just 0, so we don't worry about it. This term will be 0 because it's 0 times 3. And that equals 1/2 at squared in the x direction, right? So x equals 1/2 a sub xt squared. And then we solve it for a sub x, multiply it on both sides by 2 to get rid of that 1/2. Divide both sides by t squared. And we find that the acceleration in the x direction equals 2 times x over t squared. The x is the 1.3 meters. The t is the 1.01 seconds. Plug it in and you'll calculate the acceleration. So it's just like all the other problems with the kinematic equations. I looked at some equations to see which ones had everything that I know except for one thing that I don't know. This one had 2 things that I didn't know, so I didn't use it. It had the final velocity of x, which I didn't know, and it had the acceleration, which I didn't know. So this one wasn't helpful. It had 2 things I didn't know. But this one had a bunch of stuff that I knew and only one thing I didn't know. And that one thing that I didn't know was the one thing I wanted to know, which is acceleration.
Killing me on that one was there something like an instrument in your office. Every time I come up with the velocity for it, that being too large, and I'm sitting there going, the other way doesn't make sense when I try and think it through. But I don't know if I was just not wrapping my brain around it on that.
Usually in situations like that, you're just trying to make it harder than it is. Happens a lot. We overthink these things quite a lot because they look so complicated and there's a lot of numbers, a lot of equations. So learning to sort them out, kind of seeing through the fog, seeing through the trees is difficult sometimes. Any more questions on this problem, number 9? Part C. Also, you have a question on part C? Okay. So in part C, you've got this car now that it's done, it's accelerating. And instead of just going off the edge of the table, just off a flat table, they've decided to put a ramp on the end of the table so that when it goes off the edge of the table, it's going off at an angle. And then they're saying that whatever velocity you calculate in part B will be your velocity going off at this angle now instead of just flat off the table. But that means that you've essentially change the direction of your velocity so that it's partially in the x direction and partially in the y direction. And it's just trigonometry, right? You have that 35-degree angle. So what the diagram for this, the velocity diagram for this looks like this. You have your velocity up here, which is just some number that you got from part B. And you have an angle here that's theta. And you have two velocities that combine to make this velocity. We call this velocity x. We call this velocity y. And since this one is opposite the angle theta, what's it going to be equal to? It's going to be equal to the velocity up here, which is just a number, times sine of theta. This one's going to be the velocity, which is the hypotenuse, times the cosine of theta. So if you got 10 up here, then this would be 10 sine of theta. This would be 10 cosine of theta, whatever your angle theta is. That make sense? Brooke, did you have a different question? Part D, okay. So in part D, you're just taking this an extra step. So now that you know how fast this car is coming off at this angle, these Vx and Vy that you got in part C are now your initial velocities for part D. Okay, now that can be confusing because they called them Vx and Vy in part C, but in part D they become your Vx naught and your Vy naught. And then you're doing kinematics in 2 dimensions. So we split it into 2 dimensions. We have our x dimension, which we'll do in blue, I guess. We have our y dimension, which we'll do in green. So this is going to be now Vy0. V sine theta. Right? X dimension and y dimension. Right? In the x dimension, we know that our Vx, we know Vx0 equals V cosine theta. We also know that our initial position, x0, we'll call that 0. We'll say that at the top of the table, here's our table with our little ramp. We'll say that where it takes off at the ramp there, we'll call that x equals 0, and we'll call it y equals 0 as well. And then this distance that it falls is going to be negative some distance x, which is our final. Because it's going to be below where we start, right? Where it lands. Because it lands way over here at some distance below the table. So that will be, no, that's not x, sorry, that's y. Right? Our distance x this way will be just some distance x. Sorry about that. So this is also y equals 0. This is our coordinate system spot, right? And so this distance here will be negative y. The important point is that we know that x equals 0 starts right there. And then in the y direction, we have Vy0 equals V sine theta. And its beginning point, that the y naught, or the 0 point, is 0. And the final y is given to us as well. We know that our final y is whatever it is. In my problem, it's negative 1.9. But in yours, it's something else maybe. But we know these things, right? We don't know the final x. We know the initial x. The final x is something they're going to ask us later in the problem. X final is going to equal something we don't know. But the thing that we really want to know, that we don't know yet, is the time. That's one of the things they ask us. They're asking us for the time somewhere. Well, they're not necessarily. Let's see. Are they asking us for that? I can't see it.
On the right side, because we scroll right.
I can't. Oh, there we go. I can scroll right. So they want to know the time, and they also want to know the distance in x. So those are two things that we don't know up here. Time is not equal 0. Time equals question, right? We need to know the time, and we need to know the x. And this is the stuff that we've got. Well, in this problem, we know a lot of stuff. And so we can use this stuff to answer the question, how long is it in the air? So we need to find an equation that has that information. The equation that has information for time, there are two equations that have information for time in our kinetic equations. One of them looks like this. It looks like velocity final in the y direction equals velocity initial in the y direction plus acceleration times time, but our acceleration is g, so we do minus g times time, like that. But in this one, we have to know the final velocity, which we don't know. Do they ask us to calculate it? They don't. So we know the initial velocity, but we don't know the final velocity. So this one won't help us unless we calculate the final velocity. But there's another one, which is the initial position, or the final position in y equals the initial position in y, plus the velocity initial in y times time, plus minus 1/2 gt squared. In this one, we know g, we know velocity y, we know initial velocity, initial position y, we know final position y, we know everything except the time. So in part D, we can use this equation to solve for t, because we know everything else. But this is a quadratic equation, so it's a little bit tricky. What we're going to try to do is get this into the standard form so we can use the quadratic form easily. And we're just going to essentially put this y final on the other side and then rearrange it. So we're going to subtract y final from both sides, and we're going to get this new equation. I'll put it over here so it's a little easier to see. So our new equation will be 0 on the left-hand side, and on the right-hand side we'll have y0 minus y plus v naught t minus 1/2 gt squared. We'll rearrange this into standard form by putting the t squared part first. So it'll be minus 1/2 and g times t squared. And then we put the t part next, plus v naught t. And then we put this stuff last. Y naught minus y. So we have something times t squared. This is the something that is times t squared. Something times t, and then a constant term, right? And in the quadratic formula, the thing that's multiplying the t squared is what we call a. The thing that's multiplying the t is the thing we call b. And the thing that is constant we call c. And then we say that t equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And we plug those numbers into that formula to calculate t. It'll give you two values for t. One will be positive, one will be negative. You choose the positive one. Then, once you know t, you can calculate the distance next. Because it's just a constant velocity, it's just velocity times time in the next direction. And you can calculate that distance in the next direction. Now, for those of you, and I would wager heavily that it's most of you, maybe even all of you in this class, who are frustrated with the difficulty of this homework and the amount of times you've done a problem and had to redo a problem, and the amount of times you thought you understood a problem and then gone back to it and not understood it. Recognize a couple of things here. You're not alone. This is that hard part of the class that is so difficult. And we'll have a couple of chapters like this. I'm not here to bust your chops and bust your butt and give you a hard time. I'm here to help you through it. And then when we get through it, things will go a little easier for us. So stick with it. Ask lots of questions. Be patient with yourself. Be patient with me, because every time I explain it to you, I'm going to try to figure out what I can do to help you understand it better, but I may not succeed at first. I usually have a very high success rate, but sometimes it takes a couple of times for me to explain it in the best way for you to understand it. It's an extremely difficult thing to explain something that you understand to someone who doesn't understand. And so I do the best that I can to try to get around that barrier, but it's still challenging. Does anybody have any other questions about this problem that they want to ask? Okay, does anybody
So
have?
what are all the cinematic equations? Kinematic equations?
Good question. I like to give,
I'm pretty good at algebra.
well, that's good because algebra is easily the hardest part in this whole class. There's no question about it. But let's take a look at all the kinematic equations. Let's see. There we go. So these are the 5 basic kinematic equations that all the rest of the kinematic equations can be derived from. Them all from. So these ones are written out in the x direction. So we have x equals x naught plus dt, where the v is an average velocity, right? And that one really only works when you have an average velocity to calculate. How can you calculate the average velocity? Well, you can take your initial velocity plus your final velocity divided by 2. That'll give you your average velocity, and then that'll work. So those first 2 equations work well together. But if you don't have the information for those first two equations are kind of on their own. Okay? Then we have these last 3 equations. Velocity equals velocity initial plus acceleration times time. And that is in the x direction. Right? In the x direction, we use, so that would be v sub x equals v0x plus acceleration of x times time. It also works in the y direction, but usually in the y direction our acceleration is because of what? Gravity. So we replace acceleration A with negative g. So we get velocity equals velocity in the y direction, final, equals velocity initial in the y direction plus a minus g times t. So it ends up being m minus gt instead of plus at. Right? And then the last 2 equations are the more complicated ones. You have initial position, final position equals initial position plus initial velocity times time plus 1 half AD squared. And then you have the final one, which is the final velocity squared equals the initial velocity squared plus 2 times acceleration times the difference in position. Now, I like to write them side by side in x and y. So let's do that. There's another one that you can, there are other equations that you can create using these equations by doing some substitutions and manipulations, and we'll look at those really quick too. Those are found in the previous chapter. I like them just because they're sometimes useful. Section 2.5. Let's see here. So here are the x equations. Oh, that's all right. I'm trying to find the one that, there's one that they make from the other ones that they show us once. I'm trying to remember what it is. Not that one. Um, not that one. That's okay. Yeah, whatever. So let's go back here to this section. So here are our kinematic equations in the x direction where we have a constant acceleration. And I like to write them side by side, so this will be my x, my set of x equations, where I have x equals, this is final position equals initial position, plus the velocity average in the x direction times t. And then to calculate the velocity average in the x direction, if I have my final velocity, or my initial velocity in the x direction, plus my final velocity in the x direction, and I divide it by 2, I can get that average velocity. I can also rearrange this first equation to calculate my final velocity in the x direction to get this equation. Final velocity in the x direction equals, and this is just a definition, delta x, which is x final minus x initial over time. That's another way to calculate your average velocity.
So what is the first equation once that acceleration?
But the first equation is calculating your, it just can calculate your final position if you know your initial position and velocity, average velocity times time. That's all it is. It's just, it's like driving down the road, going 50 miles an hour for an hour. How far do I go? Right? 50 miles, that's that equation. It's just distance times time, and then if you want to know where you're going to get from where you're starting, which is the next one.
And this is constant velocity, that's constant velocity at x5, right?
This is using an average velocity or a constant velocity, right? So if you use an average or a constant velocity, then all three of these equations are valid. That's why we put the little bar over the Vx. That means you have to use an average velocity. If your velocity is changing and you don't put in the average velocity, then these equations are useless. But they're still very useful with the average velocity. Now, if you just know the initial velocity and the final velocity, and it's changing in between because of a constant acceleration, so A is equal to a constant, then you have some other equations you can use. You can use this equation, V final in the x direction equals V initial in the x direction, plus acceleration times time. You can also use the final position equals the initial position in x.
That's if acceleration is constant.
This is if the acceleration is constant. That's right.
So like in that car when we were doing, the acceleration is constant, right?
That's correct.
So we can use it out on
That's correct. Well, with the, you can use, when the acceleration is constant, you can use any of these equations, but in these three equations, the velocities that you use, sorry, that's not true. These velocity Vx's that you use have to be averages. So you have to use one of these two equations to calculate the average velocity before you can use this equation. Unless the velocity is constant. If the velocity is constant, you can use them all the time. But then the last part of this equation is the 1/2 times a times t squared, right? In the x direction. Then you have one more equation that is a kinematic equation. That's the velocity final squared in the x direction equals velocity initial squared in the x direction plus 2 times a times your delta x, which is your x final minus your x initial. In the y dimension, you have all the same equations. In the y dimension, you also have y equals y naught plus y vyx average times t. That still works. And you can calculate the vy.
What's the 2x? Is that 2ax? The one down below.
This is 2a.
No, below.
also 2A. This one?
Yeah,
It's also A.
yeah, yeah, so that one's A.
Yep.
And you call it AX because that's acceleration final, right?
No, it's because it's the acceleration in the x direction. But here we have an average velocity in the y direction as well. If you know your initial velocity in the y direction, if you know your final velocity in the y direction, then you can calculate that average velocity. You can also calculate the average velocity in y by taking your final position in the y minus your initial position in the y and divide by the time. So you have two ways to do that. But then, if it is a constant velocity or a constant acceleration, or in other words, if a equals g, if a equals negative g constant, and we're in projectile motion, we're just allowing it to fall in gravity, then we get these equations: vy equals initial velocity in the y direction. Then instead of plus acceleration times time, we do minus g times time, where g is equal to 9.8. Right? Then we also have our final position in the y direction equals our initial position in the y direction plus the initial velocity in the y direction times time minus 1/2 gt squared, and then replacing the a with minus 1/2, or sorry, with minus g. So we replace a with minus b. And then we have the final equation, vy final squared equals vy initial squared. And then we have, instead of plus 2a, we have minus 2g times y final minus y initial.
Alright, so wherever your time g into these equations, right? Sometimes you put it in as positive, sometimes you put it in as negative, or you always put it in as negative. Or
When you
it's
put
like
in-
a
When we
minus.
put in the variable g, we plug it as a negative g. When we
Alright,
actually plug in the number, 9.8, plug it in as positive 9.8.
how do you do it?
You just always plug in, g is the number 9.8, it is not the number negative 9.8.
Alright, so right there you got a minus half gt squared.
So you plug in 9.8 for g, positive 9.8. The negative's already there.
Okay, so 9.8 always has to have a negative connotation.
That's, well, yes.
Big loss, take no
Yes, but we put it in before we plug in the 9.8. So we plug in the negative beforehand. And that is confusing, I agree. But it's the way this book does it. Maybe I'll go through the book one day and change it. I haven't had time to do that
Alright, can you do the the instantaneous acceleration? Those.
What do you mean by instantaneous acceleration?
No, there's no such thing as instantaneous acceleration. Instantaneous velocity.
There's also no such thing as instantaneous velocity.
Or the velocity in an at a.
So when they're telling you the velocity at a particular point,
Yeah.
so this would be number 9 again. And it would be part C, number 9.
I wrote it down, but I don't understand why them numbers get tied into it, or if it's just one of them deals where you just trust the math.
Well, that's always the case in physics. You just got to learn to trust the math. I'm looking for something that says something about instantaneous velocity. I'm not sure what they mean. Usually you have to have a graph of a function to do instantaneous velocity.
A moderately stupid question. Whereas the negative 1/2 gt squared, it's just the t that's squared, right?
Yes.
Thank you. I really screwed that up on the math.
That's all right. Yeah.
Because sometimes you're right, epsilon and then 0. It's the same.
Yeah, it's the same.
Okay.
Yeah. If you do 0 first or y first, it doesn't matter. It means the same thing. The 0 means that it's the initial. The y tells you the direction. It doesn't matter which order you put in. Some people are really picky about the order, but I'm not. I just forget which order people put in. Some books it's different than others. So. Let's see. So there's only one that I can see that might be a problem that's talking about instantaneous velocity, and that's this one. Where you throw the ball straight up in the air and they want to know the velocity at different times of the flight.
Alright, so that one right there, right? 12.
This one?
Alright. How do you know it's 45 degrees? I mean, I assumed it was 45 degrees.
So if you wanted to travel the furthest distance, what is the angle going to have to be? Well, one of the things that you can do is you can calculate the distance that it would travel at an angle above 45 and one below 45. And if you keep doing that, you'll discover that it always gets to 45. The reason for this is actually kind of interesting. Let me show you the reason behind it.
I mean, I just straight up looked at it and I'm like, well, it makes sense because you take your ballistic coefficient, you do your ballistic coefficient, you get your spin drift whenever you shoot.
The way to do it is actually to solve for the angle theta. And then figure out, and from there you can figure out that it works out this way. But let me show, there's a better way to show you really quick.
So we're figuring stuff on no air resistance. Perfect. Operating.
Yeah, so here is a simulator that shows us this idea, and it does come out mathematically, but what we're going to do is we're going to fire a cannonball, we're going to give it some initial speed, and then we're going to see where it lands. Let's throw a piano, that's more fun. But we've got a couple different things here that we can choose. We can choose the angle. We can go between 25 and 90 degrees. So let's start down at 25 degrees and see what happens. We'll fire this thing. We'll shoot a piano out here. Right. So then let's go up at 90, let's go at 85 degrees. You can see at 85 degrees, this thing, oh, it's going to hit our friend there. Not quite. At 85 degrees, this thing goes really high, but not very far. And at 25 degrees, it goes really far, supposedly. But let's take a look at, let's raise the 25 degrees up to 30 degrees and see what happens. Should it increase our distance, or should it decrease our distance? Well, we might think that it would decrease our distance, but it doesn't. It actually stays in the air longer, so it goes further. Well, let's go up to our 85 and drop it down some 5 degrees and see what happens. With 80 degrees, are we going to go further? Or well, we're going more forward than we are up, but we end up going further out, right? Quite a bit. So that's at 30 degrees. Let's go here, or that was at 80 degrees. Let's go here at 35 degrees and fire. So 35 degrees gets its way out there again. Let's jump up to 40 degrees. Actually, let's come down from here. Let's go down from here to 75 degrees. Actually, let's go to 65 degrees. So at 65 degrees, if I can get to it, come on. Let's fire a piano. Well, this is kind of interesting because we already had one that landed right about where this is going to land, right there, didn't we? Which one was it? It was 25 degrees. Those two pianos landed together at 65 and 25. Let's look at 30. 30 degrees was this one right here. Let's look at 30 and 60. Let's launch at 60 degrees and see what happens. It's going to land right where the 30 degree one landed, right between those last two. Right? If you go back down to 30 and launch, they land together. And when you solve for theta, you figure these things out. When you solve for the angle, you find out that these things land together when the two angles add to 90. So 60 and 30 add to 90 and they land together. And 20 and 70 land together. And 40 and 50 land together. And guess what? When you go to 45, they also land together. 45 and 45 land together because they're the same angle. Right? But they also go the furthest. 45 will go out further than any other one, off the screen almost. And that is as far as you can get. Because if you go up above 45, it lands closer in. If you go below 45, it lands closer in. It just goes higher or lower, right? And so you can do that one of three ways. You can do it by experimenting like this. You can actually solve for the angle theta and then plug in different numbers of theta and see that it always goes, the biggest numbers always go towards 45. Or you can use some calculus, which we don't have. So it's one of those three things. But if you notice the patterns, you can usually just guess that it's 45. Now, when there's air resistance, it's completely different. When there's air resistance, you have to shoot it a little further forward. So you have to lower your angle down. So it's usually closer to 40, 37 degrees, something like that. Because the longer it's in the air, the more the air resistance affects it.
So how, that same question, how do you figure how hard it hits the ground?
At what speed it will hit the ground, so that's your final velocity, right? You start off with it, so here are your kinetic equations. You start off with an initial velocity in the x direction. That's your v0x, and then the initial velocity in the y direction, v0y. So you're shooting it off here at some velocity v initial, and it has a v0 in the x direction, it has a v0 in the y direction. And then when it lands, it hits the ground here, and there's some angle theta initial. It lands at some theta, which means that it has some v final in the x direction, and also some v final in the y direction. Right? And you split this problem up into x and y directions, and then you use these equations to find out the final velocities, and then you plug them in here to find that final velocity in the y direction here, or that final velocity here. So you start off with this, you split it into these two using your v0 cosine theta, your v0 sine theta, right? Then you plug in these things into these equations. Because if you find v0, if you plug in v0x into one of these equations, you can find vx, which is the final one. You can use this one to find this one. And then you can use this one to find this one. You find this one using these equations. Once you've found this one and this one, then you can use the Pythagorean theorem to find the final velocity. Does that make sense? So your Pythagorean theorem says that vx squared plus vy squared equals v squared. So it becomes kind of a 3 or 4 step problem. You take your initial velocity, break it down into to x's and y components, vx, vy to start. Then you plug them into, you crank them through these equations to find your final vx and vy. Then you use the Pythagorean theorem to find your final v. Let me show these pictures to her. I'm sorry that I didn't. I should have put a camera up here on this board, but these are the kinematic equations that we've been talking about. Kinematic equations in x right here, kinematic equations in y right here, and this is what we were just talking about, where you start off with a trajectory with a velocity initially, split it into components, vx and v0x and v0y. And then when it lands, it's got some final velocity. But what you do is you use these initial velocities with these sets of equations to find the final velocities. So for this one, you use this one to find this one. Use this one to find this one using these equations. And then you use the Pythagorean theorem at the end to find that final velocity at the end of the problem.
So now we have to use the bottom equation. We don't have, well, without acceleration.
Which equation you use over here, the equations that you use over here depend on what you have in the problem. So sometimes they'll tell you the initial velocity, then you need to have the equation that uses that initial velocity to find something that you need. Sometimes they'll tell you distance, sometimes they'll tell you time. Depending on the different things that they've told you in the problem, that will determine which equation you use.
I found the DO and OY.
So you found the initial velocities in the x and y direction.
And then, so I didn't know which equation we need to find the final because we don't have acceleration.
Well, in the y direction you have the acceleration, because in the y direction it's just gravity. So in the y direction, if you have initial velocity and if you have initial velocity, you could use, and let's say you have the time as well, then you could use this equation to find the final velocity.
But in this problem, we don't have that.
If you don't have the time, then do you have the height that it travels? Okay? So if you don't have the height, but you do have the, let's see. So if you have, so this one requires height, initial velocity, and time. You don't have time, you said? Okay. So if you don't have either time or height, then there's a little trick you can use, which we used in the section on projectile motion, the very first example, with the fireworks. Remember with the fireworks, you start off at ground and then you go up to some height here and it explodes, right? Well, the velocity at this height, the final velocity at this height is equal to 0, because that's where it turns around. And remember, if it didn't explode, it would still have the same motion on the other side, just in reverse. Remember, because it always follows this symmetrical motion. So what you can do is you can split your motion in half to find the height. And you can say, just to find the height, I'm going to assume that my final velocity in the y direction is 0, right? And if I find the final velocity in the y direction to be 0, if I say that it's 0, then I can use this equation down here to find the height. And then once I've found the height, I can use this equation, actually, to find the time, right here. Or, let's see, or I can actually skip that, and if I can use this equation to use my initial velocity in the y and my initial velocity and my final velocity is 0, and I can calculate the time that it takes to get there. So I can use this equation to find the time, or I can use this one to find the
How do you
height.
make your final velocity 0?
Because I'm only doing half the problem. I'm saying from the bottom of its motion to the top of its motion. So I know at the top of its motion, its velocity in the y direction is 0. So this is,
That's true at all of your problem.
that's true if you only go from the bottom to the top in the y direction, right? That's always true. So you can use that trick, and we used that earlier in the chapter to do this. But you can always use that trick to find the time if you use this equation, or the height to use this equation, right? And then once you know that height or the time, and that time, remember that time is only going to be half the time for the whole flight. So you got to make sure that you know that. So if you find 2 seconds here, then you have to multiply it by 2 to get the whole symmetrical motion. So it requires a little bit of trickiness, but it's still can be done. But once you find either that overall height or that time, then you can use, then you got one more piece of information so you can use other equations. Especially the time. You guys have another problem in the homework you want to work on? The first question? Is that what you said? Question 1? So you have a monkey running through the jungle, going 0.27 kilometers straight south. Oh, this is one we talked about the other day, right? So what I suggested didn't work.
Oh,
Yours, make your own diagram. It'll be easier to see. So, okay.
This way.
You might put some similar instrument. I know where is the mistake.
Let me look at something really quick.
yeah, because there it gives you the hypotenuse and an angle. I mean, and the length of an angle. I mean, and
Are you talking about which one are you talking about?
that one.
Number 1.
Yeah, because it gives you
Okay.
the hypotenuse, the length of the hypotenuse. It gives you the 31.9, and then you can figure out another angle because you know it's a right angle. You take the 31.9, subtract 9, subtract 31.9, and get your other angle.
Okay, so
That's
let's.
the angle of your hypotenuse.
Yeah, let's do this one really quick together, because this one can be a bit confusing just because of the geometry of the problem. So the hint that they give you is to draw, if you click the suggestion button, they say to make your own diagram so you can see the geometry. The geometry is confusing. So in this case, let's take a picture. Let's make a picture of it.
Yeah. See, the monkey goes north, it turns this far, and then goes this far.
Okay. So, and by the way, this class will be recorded today, so I will post it up on YouTube if you want to see this.
Figure it out. Figure this out.
Maybe it'll go viral.
Figure this out.
Okay, this problem has a monkey running, running monkey. So in this case, it's going east, then it turns south, then it goes in that. So okay. So it's going to so I'm going to draw my coordinate system up here. I have north, and then I have east this way. So my monkey is originally going east, and then turns towards the south, like this. So I got 2 vectors, right? And my first vector is some distance east. I'll call that some distance in the eastern direction. And then I'm going to have some distance in the southeastern direction. But what they say is that he turns a certain amount of angle towards the south. So it goes, he's going straight east, then turns 44 degrees toward the south, which means you take your angle from the east towards the south. So that's my angle theta right there. Now, if you were doing this, there are different versions of this problem. If you started off going north, for example, and it says that you turned west, then you would measure your angle from the west to the new place. So maybe it's 54 degrees towards the west. That would be your angle there. Regardless of how your problem is done, you need to make sure that that angle is measured correctly.
Why do you use
I'm
the
just,
distance east?
yeah, my distance in the east, my distance in the south. But what they want to know is they want to know your total displacement, which is this vector here. Right? They want to know the total thing there, and you go, wait a second, this is not a right triangle. Dang it. So you make the right triangle. What I'm going to do is I'm going to make two right triangles. At the end of my two sets of arrows here, I've got this point, and I'm going to make a right triangle by drawing this line up to there. If I was doing this problem, I would make my right triangle by drawing a line from here to here. Right? Go from my end of my last 2 points and draw a line from here to here. And that's going to give me two right triangles, this one and this bigger one. And this one, it's going to be this big triangle all the way around on the outside, and then this smaller right triangle. Why do I want to do that? Because then I can use this big right triangle to calculate this side, which is my displacement, which is what I want to find. So that's my displacement. And what it's going to be is it's going to be this whole side up here squared plus this side over here squared. Well, this whole side up here is two parts. It's this part and this part. This part I already know, it's dE. So this one's going to be d sub e plus this side of this triangle. And then this side of the triangle is just going to be the side of this other triangle. So this triangle right here is the key to it all. We have angle theta. We have this side which is opposite that angle. And we know the hypotenuse. The hypotenuse is dSe over here. So I use this triangle here to figure out the rest. This side is the adjacent side to this, so this side is going to be dSe times cosine of theta. Because it's adjacent to that angle. That's this side right here. So I'm going to add that to my dE to get this whole side over here. So that's done. And then this side over here of this triangle is dSe, d south, and my distance in the southeast direction, times my sine of theta. Okay, and that's the other side of my big triangle. So my big triangle here has this side, which is equal to this, has this really long side, which is equal to all this. And if I square this and add it to the square of this, then I will get the square of my displacement. Does that make sense?
The cosine is
Is the adjacent side.
adjacent over hypotenuse. Sine is opposite over hypotenuse.
That's right. So when I did this adjacent side, I used the cosine. When I did the opposite side, I used the sine.
Cosine is adjacent.
Yep.
And then sine theta equals opposite over hypotenuse.
I didn't show the camera on that. I'm not very good at this right now. But that's the geometry we just did. I need to remember to turn the camera back on the board. So this is our bigger triangle. This is our original displacement, our second displacement, we traveled east and then we traveled southeast. The angle theta, which is the angle that we turn towards the southeast. And we wanted to find this side, so we made this bigger triangle, which is a right triangle, and this smaller triangle, which is a right triangle. We were able to add our original distance plus this side of the small right triangle plus this side of the other small right triangle, square those diagonal in.
The hypotenuse past cosine theta equals adjacent. Hypotenuse sine theta equals opposite.
Yes. Now, does that mesh with what you did? That is what you did, and it's looking incorrect. So what we need to do is look at your numbers and make sure we're plugging those numbers correctly. I will do that really quickly. Okay, so you've got 0.182. That's your north. And then turns 85 degrees towards the east. Bring me your picture, Milosh.
Hey, are we allowed to use these notes on the test?
If your notes are taken inside the book, yes, but otherwise, no.
How do you take notes inside the book?
You can either print it off or you can download it as a PDF and
So if I download it to the zip drive and then put all these notes in there?
for what? For the whole thing?
Yeah, 182 plus 187. That's one here I got.
It should be, let's see, this should be 182. So we should get is 182 plus 182 plus the other one, it's 198 plus 198 times, and then we want sine 5 degrees, right? And then it's 199. And we'll square that. Okay, and then we have 198 times sine times cosine. 198 times cosine 5 degrees equals 197. Right? So then you square that.
199.
And then we add
199 squared.
39703. And take the square root. Here's the square root. Okay.
I did the one side of the paper. You want your velocity at the end, right? So you don't
280.
so velocity.
Yeah, just some calculator. That can be done easily with calculators. Okay. All right. Does anybody else have a problem that they want to look at? A particular problem from this homework set you want to look at?
I would like to look at, number 15.
Number 15. Okay. Let's take, oh yes, the cannonball. So this is a great example of how we can separate out the different things here. So we have a problem where we're shooting a cannonball at different heights and at different speeds in the x direction, but different heights in the y direction, right? And the thing that they're asking for is, we want to know the shortest to the farthest horizontal distance before hitting the ground. So what we're trying to solve for is x. We've got this cannonball coming out, and we want to know how far it's going to move in the x direction. In our kinematic equations, we have several equations that will tell us how far it goes in the x direction. We have this one, which will tell us how far it's going if we know the velocity, which we do. It's an average velocity because there's a constant velocity in the x direction. So this one will tell us how far it goes. This one will also tell us how far it goes, which is pretty much the same equation as this. This one will tell us how far it goes.
But we don't have time.
We don't have time, but we're getting there. And so there's a lot of things we don't have. This one will tell us if we have the time. This one will tell us if we have the time and initial velocity, right? And this one will tell us if we have the initial and final velocity and the acceleration. But the acceleration in the x direction is 0, so this one's not really helpful to us. So we have our choice between this one, and this one. Well, I would like these ones better because they're simpler, right? This one down here is kind of crazy, so let's not mess with that.
Now, since a cannonball is being fired, is the VX final that's hitting the ground, right?
Well,
But don't you use, whenever you're going VOX and VX, don't you assume that VOX, that it stays the same, the velocity in the x
that's
direction?
right. In these problems, the velocity is going to stay the same in the x direction. There's going to be no acceleration in the x direction. So that's why this one is good, because if it stays the same, then we can use this number. We can use our velocity right here. This is either an average velocity or a constant velocity. So that works. So this is the equation that I want to use. What's that?
You don't have time.
We don't have time, but we're going to use this equation anyway. In the y direction, what do we know? In the y direction, we know where it starts and where it finishes because we know the height of the table, right? So we know the initial y and the final y. We also know the acceleration in the y direction, right? We also know the initial velocity in the y direction, which is 0.
So we're going to use that, we're going to use the y.
We want to use one of the y equations over here to find the time. We know initial velocity, which is 0 in y, because it's going only in the horizontal direction in the y. So we know initial velocity, and we know initial and final position in the y direction, and we want to find we want to know what is the time. So which equation are we going to use here? It's probably this one. This one has initial position and final position, which we know, because we know the height of the table. It also wants to know the initial velocity, which we know, because it's 0. So we'll use this equation right here to find the time. So it's a two-step problem. We find the time using the stuff in the y direction, and then we use that time to find the distance in the x direction, right? So we have two equations. This equation, x equals x naught plus bxt, where this is just a constant velocity in the x direction. And then this equation here, y equals y0 plus vy0 t minus 1/2 gt squared. Now the beauty of this second equation, and even the first equation has a 0 in it. We're going to say that our initial position on the edge of the table is going to be our 0 position. Here's our table. We're going to call this x equals 0, y equals 0. X initially equals 0, y initially equals 0. So that means this goes to 0 and this goes to 0. Right? Also, our initial velocity in the y direction is equal to 0, so this goes to 0. Right? So now, the only thing you need to know is time and our final height from this equation. Our final height is the height of the table. So the height of the table, if the height of the table is 1.5 meters, for example, then this is 1.5 meters below this. That means y equals negative 1.5 meters.
Why does the BY of B go to 0?
Because it starts off with no, it's not falling yet once it gets fired.
So it starts off with velocity of 0.
That's
so
right.
It starts off at the top.
It starts off, when it comes out of the canyon, it's moving forward, but it's not moving down yet. Right? It's just about to fall, but it hasn't fallen yet. So once it comes out of the canyon, it has 0 velocity in the y direction. Right? So now we have two equations, x equals vxt, and y equals negative 1/2 gt squared. Well, we need to know t. So what we do is we solve one of these equations for t and plug it into the other equation. But we need to know x, so we need to keep this equation kind of intact. So what I'm going to do is I'm going to solve this equation for t. Multiply by 2 on both sides, it gets rid of that. Multiply by a negative on both sides, it gets rid of that. Then I divide by g on both sides, gets rid of that, and I have t squared equals negative 2y over g. And that means that t equals the square root of negative 2y over g.
Yeah, but isn't negative 2 y, isn't y, g, gravity?
No, y is the height of the table. G is gravity. Now that I know this is going to be the time that it takes for each cannonball to fall. To calculate the time that each cannonball is going to fall, you're going to plug in the height of the table for y. And it's going to be a negative number. So you're going to put, if it's a 1.5 meter table, you plug in negative 1.5 right here. And then you divide by g 9.8, and you're going to take the square root, and you will get the time. Okay? But then I'm going to plug that time into this equation. So that x will equal the velocity x times square root of negative 2 times the height of the table, which is negative, over g. And that's how you calculate each distance for each one of those problems.
You say it's possible to have to solve for t in the y direction because of the gravity being constant?
What was your question?
You said it was common to
Yes,
you know,
yes.
have to solve for t in the y.
Yes. Because of the constant velocity, the constant acceleration in the y direction, you can often, usually you can solve for t using the y side of the kinetic equation. Using all your y information, you can solve for the time, and then that time can be using the x. So that's exactly what we've done here, and that happens a lot. But all I did here, all I really did here is I recognized that there was an equation in the x direction that could get me what I needed, if I knew time. And that there was an equation in the y direction that would give me time using what I already had. So then I took both those equations and solved them. I solved the y equation for t, and then I plugged it into the x equation, and I got an equation for x. So that my final distance in the x direction is equal to the velocity that I have in the x direction for each of those problems, times the square root of negative 2 times the height of the table, where the height of the table is a negative number. You always put in a negative number for that because the height of the table is below where we start, so it's negative. And then divide that by gravity 9.8 and take the square root. And you're good. And now we'll calculate the distance it goes for each situation. And then you just plug in the numbers for each table and find out which one's the farthest, which one's not the farthest, and arrange them in order. And And this is where you see the beauty of solving an equation without numbers in the first, because then you only have to solve this equation once and plug in numbers. If you do it each time, then you have to solve it however many times, I don't know how many, 8 of them or something like that. You have to solve it 8 times and take 8 times as long to do this problem.
Is that a plus in between the half you have marked out or a T?
I'm sorry, what?
Is that a plus in front of the negative half GT squared?
Yes. It was a negative. Then I multiplied both sides by negative to get rid of that negative, and so that's how it became a plus. It started off, that equation started off as y equals 1/2 gt squared, negative 1/2 gt squared rather. That's how that equation started, and then I multiplied both sides by 2 to get rid of 1/2, and multiplied both sides by a negative to get rid of the negative, and then I divided both sides by t squared to get just, or sorry, by g to get t squared on the right hand side.
So you're supposed to times both sides by a negative 2, right?
Yeah. I multiplied both sides by a negative to get rid of the negative on the right hand side and move it over to the left hand side. You can also divide by a negative, it does the same thing. Sorry, I'm not hearing everybody very loud and nodding a lot today because I didn't sleep very well last night. I used to not sleep well because I had elevated blood pressure. Not really high, but elevated enough that I couldn't sleep very well. But now my blood pressure is low, and I still can't sleep very well. I'm tempted to take blood pressure medicine just to help me sleep. But taking blood pressure medicine actually knocks you out if your blood pressure is low. If blood pressure is normal now, you take blood pressure medicine and just pass out.
So to add that YO and that VOYT back into it, you really can't do it because of the T. Well, you could, but it changes the whole equation.
And,
That's just to figure out time, that doesn't figure out height.
no, the height is giving you the problem, but the distance in x.
X equals BXT.
Yeah.
Right.
So once you find out what t is right here, then you can plug the t in right here, and it'll give you how far it goes. So that's what this bottom equation is. This bottom equation tells you the distance.
Yeah, because your X,
Because x is the distance.
X initial, X subscript
Is
your X initial plus VX,
yep,
constant velocity X prime times T equals X.
yep. And your x initial is 0, so that goes away.
So each one you got to do 2 equations to solve.
No, each one you can do one equation because I combined the 2 equations into one equation right here. This equation combines, this is t right here. This part right here is t, and that is Vx. So in the end, this is what you can do. In the end, you can take your final, well, In the end, you can calculate your final distance in the x direction by taking the velocity in the x direction, multiplying it by the square root of the height of each table, times 2. So if your height is 2 meters, just multiply by 2, and then divide by 9.8 meters per second squared. And that will give you the distance it travels. Okay. So I combine both equations into one equation, so all you have to do is just solve one equation at a time. You just plug in the velocity, so if your velocity in x was off of one table was 7, then you multiply 7 times the height of the table times 2, divided by 9.8 meters per second squared, you're done.
So what we're doing is function equation, pretty much.
Yeah, what you have done just now is you've created,
You did f of g of x.
yeah, exactly. You've created a function that will calculate the distance from a couple of other functions that calculated time and distance. It's exactly what we did. We did a composite function. Is what that's called. That's a good connection to make. Not many people make that connection, so you should be happy that you made that connection. It's a good sign that you're understanding what the math is doing. So many people just kind of go through the rigmarole of the math and just say, okay, I did the algebra. They don't necessarily understand why it works. And that's good to understand it because it means your mind's quick.
What I'm having the most problem with is identifying the final and the initial, and actually, like because your VOX squared plus your VOY squared equals your,
V final or V initial squared,
yeah,
which is the Pythagorean thing.
yeah, and then like to tie in your final and your initial, well, it changes.
Yeah,
Like
yeah.
it depends on what the question is asking,
Mhm.
what you plug in. I mean,
Yeah, and that's hard to sort out sometimes because that's all about organizing numbers. It's not necessarily math. That's organizing numbers, which is why we draw the pictures, which is why we split it up into X and Y's and write things down and try to make sure that we understand. The organization of these problems is easily the hardest part. Figuring out what is easily the hardest part of these problems.
it's like taking the data and assimilating
Yep.
it into the problem, but then you also have to conform the problem to the data.
Yep. That's exactly right, and that is the hard part. And that's why we say that this class is more about learning how to solve problems than it is about physics. Because this is what all problems are about. It doesn't matter what kind of problem it is. It could be how to plant a cornfield. It could be how to, make money in your restaurant. Every single problem in this world, even when you're talking about, how to teach your kid how to tie his shoes, every problem that you have to face in this world is about breaking down the problem into the information that you have, the information that you want, and figuring out how to get from the one to the other. And organizing it somehow and creating a structure that's going to help you to solve that problem. That's what problem solving is about. And this class, more than any other class that you'll ever take, I can almost guarantee you, is the best class for that kind of problem solving. Because it really challenges you at a level that you've never been challenged before, with stuff that you've never used before. So you have to really think about the problem solving aspect. Now, if you go on in engineering or physics, you'll get a lot more experience with this. You'll see it a lot more times, and you'll get it's like secondhand nature to you all the time. You think this way after a while. But every problem needs to be approached. For example, a couple of years ago, I did this class with a bunch of other faculty members here on campus where we were supposed to learn how to be leaders. How do you learn how to be a leader? I'm not sure. But anyway. We were supposed to learn how to be leaders, and we were supposed to come up with a project and figure out how we were going to accomplish this project and show everybody at the college that we were leaders. Well, we could not get a project out of the gate because nobody in the group could figure out how to choose a project. To me, it just made sense how you do this. Well, you got a bunch of different ideas for projects, and you you sit down the pros, you figure out the pros and cons for each of these projects, you arrange them in order of, the ones that have the most pros and the least cons, to the ones that have the most cons and the least pros, you essentially arrange them in order from best to least, and then you pick the 3 best and then you go on. Now that just made sense to me, because that's a problem-solving technique that you use in engineering and physics and science and math and all these things. They could not wrap their heads around it. Even though I had another math instructor there, he couldn't wrap his head around it. They just wanted to pick the idea that sounded the best, even though it wasn't going to have the biggest impact, it wasn't going to do the best things for the college, and maybe it wasn't even feasible. You know, some of these projects were just ridiculous. And so, it took us probably 3 or 4 weeks to figure out what we were going to do. And when we finally figured out what was the best project for us to do, all of them bailed on it because they just thought, oh, this is too hard, I can't do it. And they're like, really, am I going to do this on my own or what?
Hey, I got one question on this problem, right?
Yep.
So you got negative 2y over d.
Yep.
Alright, so you know that d is 9.8 meters per second squared.
Yep.
And you got a negative 2y, so you want your g to be negative.
No. With that version of it, the y is the height of where it's going to hit, which is the bottom of the ground, but we said 0 was at the top of the table, so y is always going to be a negative number. Because it's always going to land below where it started.
Yeah, but b is not going to be negative.
No,
I mean,
y,
x isn't going to be negative.
but y will be negative.
Alright, so it's a negative 2 times a negative.
Times a negative y, which is the height of your table.
So it'd be a negative times a negative divided by a negative.
Divided by a positive, 9.8 is positive. So that way you always get a positive number.
It's under a square root, it doesn't matter.
Yeah, it does. A square root of a negative number gives you an imaginary number. So,
Yeah, but a negative divided by a negative is positive.
but g is positive, y is negative, so negative times negative is positive divided by y. It doesn't really matter, just
Okay, I'm with you. Negative times a negative equals positive, positive divided by a positive equals positive, square root of positive equals positive,
Yep,
everything.
you do. So you just,
So you can actually, whenever you do your math, you gotta make sure it stays within the parameters of the law.
the original problem, right? Because in our original problem, we said that the table height, the tabletop was at 0, so the floor underneath it is negative. So that's why the y is negative, because it lands on the floor underneath it. So the y always ends up being negative. Now, if we said the floor was 0, then the height of the table would be positive, and we would have come up with a different answer, but it would have been the same idea. All right. Anybody else have another question on another problem? Are we done with questions for this homework assignment? Now, when did I make this one due? Tonight? Good. Should we extend that till tomorrow or maybe Thursday or something? You guys need some extra time?
I'm going to today, but we should probably extend.
Yeah, I'll extend it. We used to always say either I'm going to finish my homework or it's going to finish me, one of the two, right?
Well, it's been finishing me for about a week, so.
This homework finished me already.
I worked on one problem last night for 5.5 hours.
Oh my goodness. Send me an email.
And I kept working on it, and I kept working on it, and I kept getting different answers.
Send me an email when that happens.
What's your email?
Well, you can send it directly from the homework problem. So when you get into your homework, right here at the bottom where it says message instructor about this question, just click on that and it will send me an email. And it sends me the email with the question inside the email so I can see what you're doing already. Just do that right away. If you've spent more than a half an hour on a question and you're just not making any progress, send me this message right away. Because no matter what time of day it is, I usually will check my email every couple of hours. And if I get a question from you, I'm going to try to answer it as soon as I can. Sometimes it's not convenient for me to answer the question, so it might take a little while. But I usually try to answer it that day, and within the shortest time possible. Then just stick to the problem and do something else while you're waiting for me. I don't want you to spend 5.5 hours on a problem and not make any progress. I know what that's like. You know, I grew up doing physics in an era when access to people was much less than it is now. There were no smartphones, the internet was still in its infancy, and you had to go and make an appointment with your instructor. And they had tutors that were always available to us, which was nice, but I wasn't always at school, so I wasn't always available, you know, to go to the tutors. So I grew up in an era where 5.5 hours on a problem was normal before you could get in and talk to your instructor. But let's try to avoid that. Try to email me, and I will check that. I check every day throughout the day, except for Sunday. Sunday I take off. So if you message me on Sunday, guarantee it's going to be Monday morning before I get back to you.
So whenever we're dealing with acceleration, we're normally dealing with constant acceleration.
Yes, that's the assumption we're going to make because that's where these equations work, right?
All right, whenever we're dealing with velocity, it can be constant velocity or
It could
can
change.
be instantaneous.
That's right. If it's
You
a
cannot
constant,
use-
if
you
it's
cannot-
constant, you can use these equations.
Yeah, but you cannot use the Pythagorean theorem for instant velocity. You can only use it to make constant velocity.
The Pythagorean theorem you can use at any point in time, so you can use it at instantaneous,
But just for that specific.
but it only works at that particular point in time and space.
So it's kind of like a limit function.
Yeah. Exactly. Okay. All right. So let's change the due date on this really quick. And homework 3, we'll change it to tomorrow night. If that doesn't work, we can change it again. But now let's take just a few minutes to get a little preview of chapter 4. Now that we've gone through projectile motion in one dimension or in 2 dimensions, and we've covered kinematics in 1 dimension, and we've learned how to deal with velocity, acceleration, displacement, position, all these things. Now let's add something else. Let's throw another wrench into it and make it even harder.
Ooh, I can't wait.
I know, I love it when it gets harder. It's my favorite thing in the whole world. So all this stuff was known, for the most part, when Newton came on the scene. This stuff that we've just been doing was all work of Galileo and other guys about his time, or chumps back there in Europe. And they'd all figured this stuff out, but they still didn't really know what forces were all about. They didn't know what caused these things to move, what makes them move. And it was Isaac Newton that came along and figured that out. Incidentally, at the same time, he also figured out calculus at the same time, because it turns out that calculus was necessary to really understand this stuff. It's not necessary for us to do it, but it was necessary for him to understand it. So, we need to talk about forces, because it's force that causes things to move. So what is a force? Can anybody define a force for me in their own words? A thing that causes acceleration? Okay. In more general terms, or in more everyday terms, a force is simply,
How hard something hits something?
it's something that actually, that's not even it either. It's actually a push or a pull. Okay? So how hard something hits something, if it doesn't push it, if it doesn't actually move it, then it's not necessarily a force. Okay?
Yeah, but that would be a force of error.
It would. So force is something that is a push or a pull. Now there is no such thing as something hitting something else and not forcing and not pushing it or pulling it. So that is always going to end up being a force of some kind. But in reality, we want to talk about the fact that forces push things or they pull things in some way, in some direction. And so because they do that, they are a vector. Just like acceleration is a vector, just like velocity is a vector, just like displacement is a vector. It has some kind of a value that's associated with a magnitude or a how much, but it also has a which way, a direction, a magnitude and a direction. So here's an example of that. We have skaters here you're looking at them from above, so they kind of look funky, but You've got this skater in the blue here. They're on ice so that there's no friction. The reason that we put ice skaters on there is because ice skaters have very little friction between them and the ice. And we have the skater in the pink below here is pushing the skater, and the pink skater in the pink over here is pushing the skater. Skater 1 is pushing this blue skater to the right. Skater 2 is pushing them upward on the page here. And there are two forces. There's force 1 from skater 1, force 2 from skater 2, and there's an overall force. Look at that. That looks familiar, doesn't it? Pythagorean theorem, sines and cosines, angles and x directions and y directions. We're still going to have components in the x direction, components in the y direction. But instead of now a or velocity sub x, it's going to be force sub x. Instead of velocity sub y, it's going to be force sub y. But we're still going to be able to split this thing into dimensions, and then we can also use kinematics in this way as well, because we're splitting it into dimensions. When we have forces, multiple forces acting on an object, we often draw what we call a free body diagram. We represent the body using either a point or some other simple shape. But if it's just as simple as it can be, we represent this blue skater with the point down here, this red point. So that's our skater now. And then the two forces that are being applied are drawn as forces that move away from that point, so they point away from that point. And they're drawn as arrows. The length of the arrow represents the strength of the force, or the magnitude of the force. And the direction of the arrow, of course, represents the direction of the force. So this is a free body diagram, we call it. Also, the forces that we're going to draw on the free body diagram are only going to be the external forces acting on the body. So any forces that are acting on the body that are coming from outside the body are going to be the forces being included in our free body diagram. What forces can exist inside of a skater? Can a skater have internal forces that act on them? What's that?
Inertia.
Well, inertia is not necessarily a force, and we'll talk about inertia a little bit later here. What's that?
Blood.
Okay, blood. You know, you have forces that cause the blood to move around your body, but we're not going to include those in our diagram. But also, how about your arms? You can move your arms as a skater, but those are all internal to the skater, right? And those can affect the skater as well. They can change what the skater is doing. For example, when a skater is spinning and they put their arms out, they spin really slow. When they bring their arms in, they spin really fast. It affects what they're doing. But those are internal forces. We're not going to include those. Okay? We're only going to include things, pushes or pulls, that happen from outside the skater and act on the skater. Okay? Did you have something you wanted to say?
I thought mass, maybe.
So mass is actually part of inertia. We'll talk about that later. But and mass is a very important part to this. We call this idea of applying forces to kinematics. So we start off with kinematics, which tells us how we're moving, and then we apply forces to it, which tells us how we're moving, why we're moving, what's making the movement. We call this dynamics. Okay? So the study of Newton and his laws is the study of dynamics. So here's another example of a force. You have a spring, and you pull on the spring. And that is an external force applied to the spring. But the spring also pulls back. You've ever pulled on a spring before, you know that, don't you? Because if you let go of it, it goes back to where it was. If you pull on a spring, you can feel it pulling you back. Right? And that's true in all cases with forces. There's always some kind of force that is a complementary force, you can think of it as. So if I push on something, it always pushes me back. Right? How do you know? How many of you have ever been in a fist fight? I have. Okay? I got in a fist fight a couple times as a kid. One of them was with my older brother, who was like a foot taller than me. And it's the only time I ever broke a bone. I might have broken some ribs once, but I don't really know. I never took an X-ray. But I broke my hand because I had to hit upward like this, and I caught him right under the chin, and it caught my pinky and broke that bone right there, which is called the boxer's break, right? It's the most common bone that a boxer breaks, is that little pinky bone right there. So I broke that bone. So how do I know that I got hit back when I hit my brother? Well, because he broke my hand. right? I hurt his jaw and knocked him a little silly, but he broke my hand. He hit me back, right? So what do boxers do to avoid getting hit back? They wear gloves, right? Gloves help to extend the time of that hit so that the hit back is spread over a time. It's a lower force over a longer time. We'll talk about that in another chapter, how that works. But also boxers avoid getting hit hard by turning away. They roll with the punches, right? So if somebody's trying to hit you and you don't want to hit them back, because if they hit you hard, you have to hit them hard back, which means you're gonna get a hard hit on your face. But if you're about to get hit and you make that hit soft so that you can't hit back as hard by rolling with the punch, so you roll your head away from it so they can't hit you so hard, then you're not going to hit them back so hard, and neither of you are going to get hit so hard, right? The last thing you want to do when you're boxing or in a fist fight is lean into that, right? Or really like cringe up and because then it's going to hurt. You want to roll with the punches. And that's a physics thing. So, forces. There's some interesting forces out there. There's what we call the electromotive force. It's a force that causes electricity to move. Okay? And we'll learn more about that next semester. What other forces out there are interesting that are out there that aren't necessarily push and pull, like grabbing something and pulling it, or pushing against something with your hands? What other forces? What about the one Newton is famous for? What is that? Gravity is a weird force, isn't it? First of all, does gravity ever push? As far as we know, it doesn't. It only pulls. Right? And is contact required for gravity? Absolutely not. The whole universe is held together with gravity, and most of the stuff in the universe has never been in contact with most of the other stuff in the universe. Right? But it's all held together with gravity. You know? So it's kind of interesting, gravity. Are there any other interesting forces out there that you know about? There's an interesting force that happens. You see the effects of it when you have a comet nearby. Any of you ever see Halley's Comet? Any of you old enough to have seen Halley's Comet last time it came out? That's awesome. How about the Hale-Bopp Comet? That was maybe 20 years ago. You were children when you saw it, maybe. So when a comet comes close to the sun, what starts to form behind the comet? The tail. But then as it gets really close to the sun, it actually kind of is on the side of the comet. So the comet's moving this way, but the tail's off this way. Right?
So it's the only way you can see.
Nope, it's not light.
Light pressure.
But actually, the light from the sun is actually pushing the comet. So it turns out that light actually can force things, can apply a force to things. It's kind of a weird force. And Einstein, again, Einstein will mention many times in this class, Einstein was one of the people that suggested how this works. And he did that with a guy named Bose, actually, that from the Bose rate radio, named after that guy. But anyway, Einstein and Bose figured this out back in the 1930s, but they couldn't really prove it because we didn't have bright sources of light that were available to us at that time that were sources we could control. Eventually, when the laser was invented, they were able to show that you can actually push atoms around using lasers. But it was not even Einstein, the first one that suggested that that's why comets do that. It was actually way back. No, who was this? I want to say it wasn't Kepler, it was...
It's been Galileo.
No, it was about the same time, but it was a scientist, I think, I want to say he was Danish. But anyway, there's a scientist way back during the time of Galileo that looked up there at the Halley's Comet and he said, you know what, I'll bet you it's the light is so bright it's kind of like wind. And it's pushing on the tail of the comet. And that's kind of what it is. So there are lots of interesting forces out there, some of which we don't really know much about. In fact, we really don't know much about any kind of force. Forces are mysterious to us, but we do know some things, and we're learning more every day. So Newton, as he started studying these forces, he came up with these laws, and this was the first one, and this is the only one we're going to do today. His first law says a body remains at rest, or if in motion, remains in motion at a constant velocity, which means constant speed, constant direction, unless acted upon by an external force. It says net external force, that means all the forces add together that are acting on it add up to be a force that is not zero. So, for example, if I push on you this way and the friction from the chair pushes you back this way and you don't go anywhere, the net force is zero because you haven't gone anywhere, right? But if I push you really hard and you fall over that way and you go to the table, then that's a net force, right?
That's what the lawsuit
That's
goes.
right. I've got insurance. As long as I'm in this lab, I'm covered. But this is what we call inertia. And this has something to do with our mass. Things that have more mass have more of this inertia, have more of this ability to keep doing what they're already doing, to stay still if they're staying still, to move if they're moving, to keep moving if they're moving. And the way that we measure the amount of inertia you have is you measure your mass. The more mass you have, the more inertia you have. Plain and simple. And that's the first law of motion. It seems pretty straightforward, but you know what? Nobody had really ever thought about it much until Newton came along. So it was really groundbreaking. Newton's first law of motion. We'll come back next time and we'll learn more about his second law and his third law, and we will learn about the mathematics involved with those, combine them with the kinematics, and make some problems that are even more fun than the ones we did in China. I promise you it does get better. Even just having survived chapter 3 will make it better for you, I promise. All right, so I will be available today for homework questions if you have them, if you're going to work on homework. So make sure you come and get me if you have questions. Don't waste too much time on any given problem. Get help. And make sure that you email me from your homework if you have questions. I will stay close to my email. And chapter 4's homework will not be due Thursday. We will push that off probably till next Tuesday.
I like having the homework due on Tuesday.
And that's fine.
Because it gives me all weekend to
That's perfectly fine.
That's because you're losers. That ain't cool.
Gives- Gives me all weekend to recover so I can do it again on Monday, right? All right, we'll see you guys later. Have a good one. I will post this on YouTube, the videos that I take. Whenever I take a video because somebody's gone, I will post it on YouTube. I have a channel called MPCC Engineer. If you go to that channel, you'll find a playlist called Physics Fall 17, and it will be there. So